All right, folks. Today, finishing up chapter 3, talking about series. So, just for clarification, so let's say we have some sequence 1, 1/2, 4, or 1/4, 1/8, 1/16, etc. Notice there's commas in between each of those terms. That tells me that's a sequence. If I were to put addition symbols in between each term, this is now a series. And if there is no ellipsis at the end, that is a finite series, or the vocabulary the IB uses, we call it a partial sum, because it's the sum of part of the series. And since there are 5 things that are being added up, 1, 1/2, 1/4, 1/8, 1/16, we'd say that is the 5th partial sum. So we'd use like the subscript 5 there to indicate that we are talking about the 5th partial sum. Is everybody okay with the vocabulary there to start? Just as a quick aside, what type of sequence is that? 1/2, 1/4, 1/8, 1/16? What was that? Somebody mumbled something. Geometric is correct. How can you tell? Multiplying by 1/2 to get from one term to the next, right? Everybody cool? Okay. Since that's a geometric sequence, Sn then is a geometric series. Everybody's okay? All right. So, as you might imagine, we're going to want to cook up some notation for this because nobody wants to write down 75 things added together, right? Like yuckarooskies, like nobody wants to burn the pencil lead and take the time to do that. So what we do is we use something called sigma notation or summation notation. You can use those 2 terms interchangeably, they mean the same thing. So for example, if I have the 5 terms of the sequence A1, A2, A3, A4, A5, I want to talk about the 5th partial sum of that sequence, I'd be talking about A1 plus A2 plus A3 plus A4 plus A5. Now, that's a lot of writing, potentially, and if you imagine if it was 50 things or 100 things or 10,000 things that we're adding together, like nobody wants to write all that nonsense down. 5 is doable. 10 is annoying. 100 is like, get out of town, I'm not doing it. So what we'll use is we'll use this summation notation, or sigma notation. So this big E-looking symbol here is the capital Greek letter sigma. So the way we describe this partial sum with a sigma notation is we declare a index variable, typically I or K or N are kind of like your canonical letters you can choose, but it doesn't really matter. You can choose any letter you want. Since we started adding at our first term, I'm going to say I is equal to 1. And because we ended adding at my 5th term, we'll say that the upper bound is 5. And the things that we're adding up are this sequence, A sub I. So if you look at my A's, the thing that's changing is the subscript. So that's where the index variable is placed. Is everybody okay with that? We'll do some more examples of writing summation notations here in the rest of the lesson, but I just want to give a little quick jog your memory, because ideally you've all done this before in your pre-calculus course. So this will be one of the things I'll expect for you to be able to do on the test, is be able to expand the sigma notation into a partial sum, or take a partial sum and condense it into a sigma notation. So let's do a little bit of practice here. So our first is the sigma notation here. So we're starting at I equals 3 and ending at I equals 6. So we're going to consider I equals 3, 4, 5, and 6. should have 4 things. Where are those i's going to be plugged into is the sequence I squared. So we'd have 3 squared plus 4 squared plus 5 squared plus 6 squared. So that's me just expanding my sigma notation. If I asked you then to calculate that, you could just type those 4 things in your calculator, press enter, and like, whoop-diddy-doo, no big deal, right? Does everybody feel good about how I went from the sigma notation into that expanded form? Or into its partial sum? Okay? So here, I have a partial sum, right? Everybody agree? So I can write this now as a series, or I'm sorry, as a sigma notation. So if I look at the terms of this series, what part is changing? The exponent. What part is staying the same? The base, right? So seems to me that that's the way my terms of my sequence should look, right? Everybody feel okay there? Now what value, or what value of I should we be starting with? 3. So we'll have I equals 3. And what should we be ending with? 7. Perfectly valid way of approaching this. Not the way I would have intended for you to do it, but it works. This is fine. When I look at this, what type of series do I have here? If I look at the terms 3 cubed, 3 to the 4th, 3 to the 5th, 3 to the 6th, 3 to the 7th. That's geometric. What are we multiplying by each time? 3, right? Because 3 to the 3rd is, or 3 to the 4th is 3 to the 3rd times 3 to the 1st, because I add their exponents. So like my r is 3 and my first term is 3 to the 1st. So you could have written this, or my suspicion would have been you would have written this as that, like it's a geometric sequence, and I have 1, 2, 3, 4, 5 terms. Now either is correct. I'd give full credit for either. It doesn't matter. Correct is correct, regardless of how you write your summation notation. They both represent the same 5 things added together. One is like we had to use a little bit of math sense to generate. The other is kind of like paint by numbers. I'm just using scaffolding on what I know about writing a geometric sequence to write the equation there from last time. So whatever you're more comfortable is fine. Everybody feel okay? Let's do the next one then. So again, let's write this in expanded form. So my sequence is 2 to the n. We start with what value of n? 0. And we end at what value of n? 5. So the first term in my sequence, or in my series, should be 2 to the 0, and then 2 to the first, and then to the second, to the third. Where am I ending at? 2 to the 5th. And again, if I wanted that actual number, what that is, you could type that in your calculator, press enter, right? It's only 6 things to type in, that's not too bad. Does everybody feel okay here? Okay. So let's do another one. We're going to condense this into a sigma notation. Now, if I look at the series here, 1/2, 2/3, 3/4, 4/5, etc., arithmetic, geometric, or neither? Just did this on the quiz. You should be able to do this, right? 1/2, 2/3, 3/4, 4/5, etc. Arithmetic. Okay, you say that? So then I should get, if I do 2/3 minus 1/2, that should be the same thing as 3/4 minus 2/3, right? The difference between those terms should be the same. So if I make a common denominator, I get 1/6 over here. If I do the same thing, I'm going to get, oops. Not the same, right? Is it arithmetic? No, can't be, right? Because the difference is not the same. Here we added 1/6, here we added 1/12. Okay, so that's not it. I'm going to erase that. Is it geometric? Well, if it is, 2/3 divided by 1/2 should equal 3/4 divided by 2/3, right? So I'll do that, and I get 4/3. And then I get 9/8. Is it geometric? It's neither, right? That's a bugger, right? Because this doesn't seem real easy to be able to write the formula for this sequence. But let's think about it for a moment. If I have a sequence like this that's written as a fraction, sometimes I can think about it still as like a arithmetic or geometric sequence over another arithmetic or geometric sequence. Possibly different, right? So if I just look at the numerators, 1, 2, 3, 4, 5, all the way up to 99, is that arithmetic or geometric? Come on in.
Arithmetic.
Yes. What's the common difference? 1. And the first term is? 1. So when I write that, I just have, plug that into the formula, I just get 5, right? If I look at the denominators, 2, 3, 4, 5, all the way up to 100, is that arithmetic, geometric? Arithmetic. Great. What's the common difference? 1, and the first term is 2. So, again, when I plug into the formula, I have like I plus 1. Okay? If I do that, start with the first term. What's the last term got to be? 99. How'd you tell? If the term number is the numerator, we're good. Does everybody feel okay there? So if you have a fraction and you need to write it as a sigma notation and it's not arithmetic or geometric, and I'm asking you to do it, you can probably write it as like arithmetic over arithmetic or geometric over arithmetic or some combination of writing numerator over denominator in terms of like sequences you can. Does that make sense? Okay. Now, if I actually asked you to find the number, you know, some of these, like not a big deal to type this into your calculator, right? But this last one, ugh, yuckarooskies. Do I want to type that in my calculator? 99 fractions added together? I'm not about that life. That seems terrible. But you know what? There's another way to do it on the calculator. So if you have your graphing calculator with you and you'd like to follow along, I invite you to take it out with me right now. Okay, so what we're going to do is we're going to type in to the calculator that last series or partial sum we just looked at, 1/2 plus 2/3 plus 3/4 all the way up to 99 over 100. So the command we want is that summation notation. To find that command, we're going to press the math button And we're going to scroll all the way down. I think on my calculator it's Command 0, where it says summation. Look at the symbol after the summation. What do you see there? That's that sigma guy, right? So that's what I'm going to pick. And now basically I'm just going to type into my calculator exactly what it looked like on my sheet of paper, with one exception. On my sheet of paper I wrote I. Can I use I as a variable in my calculator? No, because what is I programmed into my calculator as? It's that imaginary number, the square root of -1, right? What symbol am I going to use in place of I? X. Boop. How's that? Not too shabby, right? Heck of a lot better than typing 1/2 plus 2/3 plus 3/4 and keep going. Like, that's a lot of typing. I just saved myself, ooh, dog it. So if this is the IB exam, I'd write my answer as 94.8 because I rounded to 3 significant figures. Unless it asks for an exact answer, which it wouldn't on a problem like this, because I don't think even the calculator is going to do the heavy lifting to give you a common denominator here. It probably overflows what it's able to type in the denominator of the fraction, unfortunately. Because you're talking about finding the least common multiple of the digits 2 through 100. You! It'll be a big boy. All right. Feel okay with the calculator? We'll come back and do some more on this. All right. A couple of stray properties that you can use with regard to these sigma notations. So if the sequence you're summing involves some constant, you can pull the constant out to the front and just do like, if it's the sum of 2I, I can just take the 2 out, do the sum of just I, and then multiply my answer by 2. So I can do the sum first and the multiplication second, or I can do the sum of, 2 i's. It doesn't matter. Additionally, this summation operation is distributive. So if you have like the sum of 2 sequences, you can look at that separately. You can do the sum of the first sequence and then plus the sum of the second sequence, which again, computationally can be really advantageous because there are formulas to handle like an arithmetic sequence or a geometric sequence, which make life a lot easier if you can separate them out. Okay. So some formulas for arithmetic and geometric sequences. While you guys look at those, I'm going to tell you a story about the formula for the sum of an arithmetic sequence. So it involves Carl Gauss. He's one of the guys on the wall back there. So I don't think it was Germany then. I think Germany's formation maybe happened in his lifetime, maybe not, I can't remember. Germany's a fairly young country by European standards. Not like Germany and Bavaria, like they're like nation states, but they're just like, I don't know, it's Prussia at that point in the 1700s or what. But Carl Gauss is like a kid, like 5, 6, 7 years old or whatever, like in a one-room schoolhouse. Is a particularly cranky teacher that's like, all these kids are driving me nuts. I just need something for these kids to do that's accessible for kids like, very young children up to my oldest children that's going to just keep everybody busy for a few minutes so I can get some peace and quiet. So he asks all the students to add up the numbers from 1 to 100. And about 30 seconds later, little Carl walks up to the desk with his chalk slate with the number 5050 written down on it. And then she's like, whoa, what? No. It's like, I did it. I'm done. Here it is. And then the teacher's flabbergasted, like, hey, you didn't even write anything down. How the heck did you do this? Like, like he's confused as to why there's no like other work written down. There's no like other calculations. It's clear the only number written down on the chalkboard was this 5050. It's like, how the heck did you do this? And little Carl's like, well, 1 plus 100 is 101. And then 2 plus 99, also 101. 3 plus 98, also 101. So I can pair up all the numbers between 1 and 100. When I add them together, I get 101. There's 50 of those pairs, so it's just 101 times 50, so 5050. Done. Notice that that is exactly the formula there for the arithmetic sequence. It's the first term plus the last term, a1 plus an, times n over 2, so half the number of total terms you're adding, which is like the pairs. And if you're able to do that as a elementary child, that's how you end up on somebody math teacher's wall 200 years later, 300 years later, 250 years later, because you're a generational, like mathematical talent. Anyway, so we have a couple of formulas, right? Worth noting that there are also formulas for infinite sequences. Now, for an arithmetic sequence, an arithmetic series, if you're adding up infinitely many things, the answer is always going to be either positive or negative infinity. We call that divergent when we talk about sequences, if you get a non-finite value. But for a geometric sequence, you can add up infinitely many things and still get a finite answer, provided that the common ratio isn't too big. So let's think about the value r equals a half. If I multiply a number by a half, does that number get bigger or smaller? Smaller, right? If I do 2 times 1/2, I get 1, which is smaller than what I started with, right? So if I'm looking at, infinitely many terms, I'm basically going to be multiplying by 1/2 infinitely many times, right? How small, then, is that number eventually going to get after I repeatedly multiply it by a half over and over and over and over again? What value am I heading towards? Not negative infinity, because I'm multiplying by a positive number.
Infinity.
No!
0.
0 is the answer. Right? If I keep multiplying by half, it keeps getting smaller and smaller and smaller, but I can't ever become negative because I'm just multiplying by a positive number. So eventually I'm just heading towards 0. So eventually adding an extra term is like adding a 0 at the end, and it doesn't really do anything. So surprisingly, adding up infinitely many things, you can get a finite answer, which is kind of mind-blowing. So that's the geometric series formula there at the bottom, right? It's just the first term divided by 1 minus r, provided that r is between -1 and +1. And it's divergent otherwise. Again, we don't really care if it goes to positive or negative infinity. It's not finite, so we don't really care. Okay. Let's do a couple of examples and then call her quits for today. How's that sound? Cool. So we're going to look at the arithmetic series that contains 50 terms. I know my projector's making noises. It starts with 3, 8, 13, 18, etc. We're told that it's arithmetic. What's the common difference here going to be?
5.
5. and the first term is 3. So the formula for my sequence would be or that simplifies down to just, minus 2. Everybody agree? Okay. So if I want to write this in sigma notation, I'm starting with the first term and ending at the 50th term, told me in the problem. And my series that I'm doing this for is 5n minus 2. And I'm done, right? That's my sigma notation. Part B, it says find the partial sum for the first 50 terms of the series. So I'm going to use my formula that we just were looking at. So it's going to be the first term plus the 50th term, which when I plug 50 into this, I get 248 divided by 2 times the number of terms. Now I could type that into my calculator, or I could do the summation thing that I just showed you on my calculator. Either way is fine. 25 times 251. Ugh. I could probably do it in my head. I just don't want to. It's too early.
6,270.
Thank you. Everybody cool? Or again, you could type this in to your calculator and press enter, right? You could do it that way also. My recommendation for you is on the IB exam or on the test for me is you fill in the values so I can give you some partial credit even if you goof something up over here. You just give me a number and it's the wrong number. There's not really any partial credit I can assign for you. Get what I'm saying? I think I got one more example, and we'll call this good for today. Sound like a plan, man? All right, it says consider the sequence in figure 3.8. Here's figure 3.8 right here. It says F1 has 1 square. How many squares are in F20? Do you suppose I'm going to draw a picture here? I'm going to think about this as a sequence. So I have 1 square, then I have 3 squares, then I have 5 squares, and then 7, and then 9. What type of sequence do I have here? Arithmetic, right? What's the common difference? 2. What's the first term? So when I write this, shortcutting through the formula, I didn't bother to show the formula filled in and simplifying. Is that okay? So if I want then the 50th term, there we go. Oh, the 20th term. Or that. So far so good? No big deal there, right? B then says, is there a figure with 149 squares? If yes, which one? If not, why? So basically what I'm going to do is I want to see, is there some F term of my sequence that is equal to 149, right? So I'm just going to take 149 and plug it into here and solve for n. What kind of value for n am I looking for? And it will have to be positive and a whole number. If I don't get a positive whole number answer, what do I say? There's no term in the sequence that has that value. If it is positive whole number, then yes. Then in fact, there's the term number. So there we go. And no 75, so it tells me that F75 is 149. You guys feel good there? C says, find the number of squares in the first 880 figures. Oh my gosh, am I gonna draw all 880 of these figures and like add them, count the squares in it? That's insanity, Mr. Kulik. What am I doing? I'm gonna do the sum from 1 to 880 of Fi, right? Now the Fi in our case, we wrote the formula for this earlier. So that's an arithmetic series. I could use the formula, or what else can I use? My calculator. Let's just review how to do that one more time. Where does the summation symbol live? Math. And then command 0, on my calculator at least, x equals 1 to 880, and my sequence was 2x minus 1. 774400. Yeah, pretty sweet, right? Okay. D says then figure F1 has 4 line segments. How many line segments are there in F20? Well, I'm going to write a new sequence. I'll call that sequence L for line segments. So I go back up here. 1, 2, 3, 4. And then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And I'll do one more just in case, but I see a pattern already. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. What type of sequence am I working with here? Arithmetic. What's the common difference? 6. What's the first term? 4. So there's my sequence. So if I want L20 then, everybody feel good with what I did? Basically the same as the first one, right? We just have a new sequence. E says, is there a figure with 450 segments? So I add the 2 over. Now without your calculator, the 6 divide 452. Oh guys, come on. All right. What are the possible divisors of 6? 2 and 3, right? Other than 1 and 6. But if we could do 6, then we could answer the question immediately. So let's do 2 and 3. Does 2 divide 250 or 451? Or sorry, 452.
Yes.
Yes. How do you know? It's an even number, right? Okay. So the 2 works. Does 3 divide 452? Miriam, you're shaking your head no. How do you know so fast?
Because the numbers don't add up to some kind of 3.
Yes.
Okay.
So your divisibility check for 3s is the sum of the digits has to be divisible by 3. So 4 plus 5 plus 2 is 11. 3 doesn't divide 11, so 3 isn't going to divide 452. So my explanation there is that no, there is no term that in the sequence that's equal to 450 because when I solve this, the term number is not a positive number. Everybody feel good there? All right. And then our last question is find the number of line segments in the first 880. So this is like exactly the same setup, but I'm using my new formula. Again, I have an arithmetic sequence. I could use the arithmetic series formula. That's fine to use. Or I can type it into my calculator. So math, summation, x equals 1 to 880. And then 6x minus 2, 232, 40, 80. Done those. You guys feel okay on this? Again, fairly easy. I think the hardest part is being able to effectively write the sequences and get a handle on the notation, but if this is your second time seeing this, which I think is everybody's case, makes it massively easier to see it the second time, where these symbols are a little less confusing. So the test description, given a sequence of consecutive terms, identify if the sequence is arithmetic, geometric, or neither, just like you did on the quiz. Okay, some of us had a little bit of a hard time with that. I'd make sure that you go back through and look at what you really have to do. You're basically looking at, am I adding by the same amount to get to the terms or multiplying by the same amount each time to get to the next term? That's all you really have to check. Use arithmetic sequence to do currency exchange story problems. You guys breeze through those on the quiz. I think that'll be fine. That's typically pretty easy for students. From given information, find the nth term of a sequence and compute the value of the specified term. Exactly what I asked you to do on the quiz on the second page, right? Find the value of the sum of the first however many terms of a sequence, whether it's arithmetic or geometric. So you could use the formulas that I quoted for you. Those formulas were also on the quiz equation sheet. They'll be on the test sheet as well. You don't have to memorize them. Or you could use your calculator. Kind of a combination of both is usually what I recommend, like fill in the numbers to the formula for the partial credit in case you do something silly and then type it into your calculator as you press enter. Use a geometric sequence to do finance-related story problems. So there you're talking about like compound interest usually. And then convert a series in sigma notation to expanded form or vice versa. So basically the things we ran through today, right? Best preparation, getting ready for the test would be to do the review, which is the homework set for
this chapter.
Sunday, right? For Sunday. So I would advise you in the next 40 so minutes that we have in class to open up your tablet, to get out your notebook and start kind of plowing through that review. I think it's kind of on the long side. I think there's 40 questions in it. But some of them are rather quick, right? Like we kind of bulldoze through these questions rather quickly once you get the hang of them. But that would be my recommendation, is to spend some time getting comfortable with that material. the review is a great place to do that. It's the only set that I'm asking you to do for this chapter. We skipped doing, the 13, 1, 2, 3, and 4 sets in favor of just doing the review because this is a topic you've done before, so I don't feel like you probably need as much practice. And we had, people coming back and forth with Kairos and stuff. It just felt easier to just assign the one thing and just do the one thing.
Which of the following will result in only...
Oh my gosh, that is embarrassing. Anybody got questions left on any of this stuff? Bathroom?
Yeah.
Yeah, go ahead. Okay.
Why so?
Get to work then, kids.